Okay, we're back for part two here. So now we're going to look at ways of conserving heat. So insulators, these are materials that have a restricted ability, oopsies. I should keep a running record of how many times I make a spelling mistake. A restricted ability to conduct thermal energy. There we go. So we have fiberglass insulation, styrofoam, dead air space, and multi-paned windows. Those are all common. Oh, look at that. Now this one was not my spelling mistake. But so is cooling. So how does that work? Probably the best example of thermal conservation is the Dewar flask. Now, I'll show you a picture of the Dewar flask. Unfortunately, there was supposed to be a picture of a Dewar flask on your Google Doc, but I think something just didn't work when I was transferring it to a Google Doc, and I did not catch that till now. So here's the picture. So the Dewar flask, you basically have it where it's an insulated thermos. And you'll see this a lot of times in sports stores and whatnot, where they have it advertised where they can keep cold water or cold liquids cold for a certain length of time, as well as hot liquids hot for a certain length of time. And so that's kind of their bragging rights, is that it's like a vacuum sealed container that's going to help regulate the temperature of your liquids without them either losing heat or warming up too quickly. So what happens is they end up having it where there's this vacuum in between. So they have two containers basically. And I'm not sure if you've ever noticed like how, let's say if you've had a glass of water and you put ice cubes in it, you'll notice that you start to get condensation on the outside. And so this, first of all, this container design helps eliminate that. So that way you're not getting the condensation on the outside of the main bottle. And then what happens is that between these two containers, we end up having it where it's a vacuum in there. So they try to suck out as much of the air as possible. So that way there's not as many molecules to be bouncing around in here and messing with the temperature that's inside here. And so with that being the case, because there's not as much that's in contact, it makes it so that it's much more likely that much more likely that the hot liquid is going to stay hot for a long length of time compared to how it normally would. And that cold liquids are going to stay nice and cold for a good length of time. Like the ones that have a really good like vacuum seal, those and have like good quality materials that they use, those can have where they can keep the liquids hot and cold for extremely long lengths of time. It's quite impressive actually. Anyways, all that to say, what happens is they also have silvered surfaces that are in between here. And if you've watched this video here, you'll notice that at the end, I'm just going to actually kind of bring it over here to where it shows it here, is is that what happens is shiny silver is the worst in absorbing and emitting heat, which makes it ideal when you don't want to mess with the temperature of something. So that's why what happens is there's silvered surfaces in between here, so that way there's very little heat that is being transmitted or absorbed between these two containers. And so that way you could have it where you have nice cold water in here and you're out at the beach on a really hot day and you are not having it where it's getting really warm really fast because it's not being affected by the temperature outside. So what I want you to do, that's my explanation here. What I'm going to do is have it where on your Google Doc, I want you to tell me in your own words why you think that the Dewar flask is so efficient in conserving heat, and why are both surfaces of the flask silvered. So just tell me your ideas based on what I was telling you, based on what you learned in the video there. What do you think? What are your thoughts? Now we're going to also take a look at heat capacity here. So for heat capacity, that is the amount of heat required to raise 1 kilogram of a substance by 1 degree Celsius. The higher the heat capacity, the more energy that can be absorbed without it getting hot. And what's very interesting, now the temperature is going to be, what is it called? Measured in joules per kilogram per degree Celsius. So for water, we have that it takes 4,186 joules per kilogram per degree Celsius to be able to raise the temperature of water by 1 degree. For ice, you need 2,093. For water vapor, so it's already a gas, it needs 2,080 degrees, or 2,080 joules, shall I say. For sandy clay, it needs 1,381. Dry air at sea level would be 1,005. Aluminum is going to be 900. Concrete is 880. Quartz sand is 795. And lead is going to be 128. So what's interesting is that if you're to just take a peek at this, you'll find out what is going to be heating up faster. So dry air at sea level or just ocean water. Well, we know for water here, it takes 4,186 joules to be able to heat it up. That's a lot. And dry air only needs 1,005. So that means that dry air is faster, and it's actually 4 times faster. And then lead or aluminum, we know that lead right here, that's one of the fastest on this chart. Lead is the fastest, so lead is actually going to be the fastest. It's approximately 7 times faster. All right. Now, why do you suppose it feels hotter in the city than in the country if both places had the same temperature pattern for the same summer day? So what's interesting is that with the city, you have so much more. First of all, you have a lot more people, and you have a lot more machinery that's giving off heat, but you also have a lot more buildings that are perhaps absorbing and emitting heat. And so because of that, whereas in the let's say in the country, let's say farmland or something like that, yes, it can get warm there, but there's not as much to absorb and emit the heat. And so it takes a little bit more time to be able to heat up. That's why you see a lot of people who during the summer, they'll have it where they go to vacation in the cottage in the country somewhere because it's a little cooler there. So it is because, because the specific, I can spell, actually it's more like I can type, because the specific heat capacity makes it heat up faster than farmland or countryland. And then think of it this way, if you've ever gone to the beach, hopefully all of you have done that at some point, is that when you think about it, if it's a really hot day, the sand gets super hot and it can burn your feet as you're walking on it. Whereas as soon as you go in the water, it's like, feels so much better. It's a relief. And so why is it that the sand can burn your feet, yet the water can help cool things off? Why is that when they're both receiving the exact same amount of sunlight? And the reason for that is because that sand heats roughly 4 times faster. So that means temperature is higher. I am recording this video way too late at night. My brain is not working properly for spelling. So the sand is going to heat 4 times faster, so that means that the temperature is going to be higher than the water. And oopsies, we're going to take a look at latent heat. And so that's going to be the hidden heat. And what's interesting about this hidden heat is that it's the energy that's needed to change one phase to another. So that means solid to liquid, liquid to gas. And that also, what that means though is that it'll heat up to a certain point. So just take a look at this graph here, that what happens is it heats up to a certain point and then it stays the same while it's changing into a liquid, which is pretty cool. So that's latent heat. It has it where it heats up and then now it's staying at a constant temperature, but that solid is melting while out at that constant temperature. And then it heats up again, and then at this constant temperature here, it turns into a gas. And so I have a little thing here that shows that, which I thought was pretty cool, is that it just says the latent heat of fusion, so temperature remains constant as the solid turns to a liquid, and then over here, the latent heat of vaporization, temperature remains constant as the liquid turns to gas. All right, so going back here, we're gonna just quickly fill this in. So if you take a look at this graph, we have from A to B, B to C, C to D, D to E, E to F. Hopefully that makes sense as I'm going through this. So what's happening at A to B? So from here to here, we see that the ice, oh my goodness, the ice temp is increasing. And then from B to C, which is right here, this is where it stays constant. And that is where the ice melts to water. From C to D, this is this nice red line up here. C to D, that is where the water temperature increases. D to E, that's this blue line here where it stays constant. And that is where, you guessed it, that means that the water is evaporating steam or a gas. And then E to F, that's this last part here. And that's just where simply the steam temperature is increasing, that's all. So steam temperature increases. If you've ever been inside a sauna, you'll know what I mean, that you are able to have it where you can increase the temperature of a gas, of steam. All right, so last little bit here. I know that we are almost done. This video is getting long. Okay, here's what I'll do. I'm gonna quickly stop this and we'll just do one last short video.